So thank you. We're going to get started. Welcome to the CVSP lecture again. Today we have the pleasure of seeing our second enrichment lecture of the semester. It will be given by, last time I called you Jonathan by accident. Things like that happen. Joshua Norton, who comes to us from the philosophy department. He works broadly in the philosophy of physics, and I think his PhD work was on the ontology of quantum loop gravity. So if you're into crazy stuff, come talk to him. So please join me in giving our attention to Josh.
Cheers. Claps. So I'm a little bit pinned behind this thing because I actually have to stand over here to touch, but I hope to move around and to get your attentions a little bit. As Courtney said, this is the second of your public sort of lectures. I'm actually not super familiar with how this works, other than you guys are going through some material, right? And I'm lecturing alongside to kind of provide some additional benefits from the time and the culture to kind of enrich your experience. Is that correct? Something like this? Okay, thank you. Now I take it that Jihad Tuma, Dr. Tuma, if I'm saying his name correctly, he went over and he talked to you guys a little bit about the sort of revolution from the heliocentric universe to the geocentric universe. Is that right? And you see, I want to engage you. Those homeboys in the back, I'm not actually going to be able to get your attention very well. But I want you guys to be engaging me as well. I want all of us to be thinking and talking because I'm going to be asking you guys to respond to some things as we go along. Yeah, you guys. Yeah, I see you. Okay. So here we go. What we're going to be doing now is you already talked a little bit about the revolution that occurred between heliocentric and the geocentric universe. We're going to talk a little bit more about the sort of tools, the instruments which helped shape the Renaissance and the scientific revolution which Copernicus kind of helped usher in. So what I want us to focus on is what are the tools for the scientific revolution. A lot of these tools are going to be physical in nature, sort of actual things you could put your hands on, and other tools might be a little bit more conceptual or structural in nature. Now, if there's any point in the talk in which you want me to slow down or re-say something, just raise your hand. If I see it, I'll stop and I'll ask you what it is you want me to go back on. And let me know if this microphone, because I might be moving around, if you can't hear me at any point. All right? Okay. We are at the wrong part of my talk. 1 second. Just don't look at the screen. There's some fun stuff. Okay. So instruments of revolution. This is a quote by one of the early scientists. He was a geologist and a paleontologist. He says, "Beautiful is what we see, more beautiful is what we know, most beautiful by far is what we don't." And this is a good attitude. It sort of exemplifies the attitude of some of the earliest scientists. They were not too afraid of what they did not know. They were at a cusp of a sort of renewed understanding of what the natural world is, the conceptual world, a renewed understanding of their culture and their place in history. And oftentimes we, especially as we consider ourselves students, find ourselves at a similar cusp. We must never be afraid of what we don't know because that might be where the most beautiful things lie. Now we know that there are new theories that come about. How many of you have heard of quantum mechanics? Okay, oh, this guy has. General relativity. All right, that one over there does. Now, there's a problem. We can't get general relativity and quantum mechanics to work. When we get this to happen, we can't get them to work together. Once they start communicating, we're going to have a revolution in the way that we understand the natural world. We are at a cusp in our understanding of what the nature of substances, of nature itself is, of space and time is. And we should be excited to see what the sort of future advancements in science lead us into. So as each of you are getting degrees and different things, never be too sad or worried about what you don't know, because that's what makes life and education exciting. We're going to hear a little bit more from Stino in a little bit. Here's our overview. We're going to talk about astronomy. Now, you've already did astronomy in the previous lecture, so we're not going to talk a little bit about it, but we're going to focus in particular on this thing on labs by Tycho Brahe. You already talked about the telescope. I'm going to more briefly go through that. We're going to be spending a little bit more time on labs than we will on other things. We'll talk about medicine, surgery, and microscopes. Notice that I'm putting the names in parentheses because it's the individuals aren't so important as the tools which they use. Surgery, microscopes. The electroscope by William Gilbert. Chemistry, the vacuum pump. These hemispheres are going to be fascinating. We're going to talk about them. And then Boyle's law as well. The scientific method, Francis Bacon. These are the sections we'll go through. Let's talk about astronomy. There's a gentleman named Tycho Brahe, and on the left you'll see an image, and this image is a castle that he built. And this castle was one of the first state-funded scientific research institutes, one of the first of its kind, especially in Europe. So remember, paying attention to the tools, the instruments of revolution. He was the last of the major naked eye astronomers working without telescopes for his observations. Who was the first non-naked eye astronomer? Galileo, right. So he was like at the cusp right before Galileo, and his work ended up allowing Kepler to develop his elliptical orbits. His work, not Galileo's work, was instrumental for the sort of shape of our modern understanding of the orbits of the planets. This is a quote, the first competent mind in modern astronomy to feel ardently the passion for exact empirical facts. See, this is where we'll do this. This here, exact empirical facts, this is one of the key features, which is, in a sense, the spirit of the scientific revolution. This is what kind of cuts off pre-revolution, pre-Renaissance from what comes after and gives us a sort of spirit of modern science. He was the first competent mind to feel this empirically, at least from the perspective of astronomy. His observations were some 5 times more accurate than the best available observations at the time, and he did this without a telescope. So he's looking at the stars, he's looking at the moon, he's seeing how the different celestial beings, where they are with respect to the background stars. That word kind, that should be king. We'll pretend it is. King Frederick II of Denmark, he loved Brahe. Brahe was like part of like the sort of royal parsonage in a sense, and he gifted Brahe the island of Haven. How many of you heard of the island of Haven? I assume not many. It's a super tiny island, not too far from Denmark, closer to Sweden. Brahe built one of the first research facilities. I have no idea how to say these. Urenburg and later Sturgeonenburg, around 1581. Alchemy, he studied astronomy, he studied astrology. What happened to alchemy? Alchemy turned into something. What was that? Chemistry. So he was studying what we would nowadays might refer to as a sort of pseudoscience. He studied both alchemy and astrology and astronomy in the research facility. His budget was up to upwards of 1% of the national budget of Denmark. He had a ton of money going into building these research facilities. This is state-funded scientific research happening in 1581. Here's whenever you see this border, it's like a picture album. We're going to tell some stories. This is Sturgeonenburg. This was built later, and much of it was underground. His first one, Urnenenburg, however you say it, was above ground. He lived in it, and the wind would often shake the building and ruin his observations. So what did he do? He had to eliminate any sort of perturbing factors. He put it underground. He rebuilt the whole thing in his second lab. As you can see, much of this is underground. You could barely... You see in here, there's scientific instruments. We're going to be talking about these scientific instruments very briefly. These things would often open up to the stars so that the stars could come in, the light, and they could measure the location of stars against the background. This is the island of Haven, very small and flat. It'd be good for his purposes. And this is an aerial view of what's left of his labs in modern days. There was some war and someone came and tore it all down. So they're slowly rebuilding it. Here are some other pictures. This was a giant mural that he had built on the wall, and they would let the starlight come in and be able to measure the location of certain spots of light along this big measuring device. This is Sturgeonenberg, most of it's underground, and this is Uranenberg. He lived in the bottom, they did observations on the top. They would have research assistants. How many of you work in a lab? You could come and live here. Yeah, he would hire you, you would come and live with his family, you'd do observations at night. This is in Armorelli sphere. Remember, we're focusing on the material of the instruments of the scientific revolution. The original ones had 5 to 6 rings. As you could tell, each ring kind of allows it to rotate on a different axis. The problem with lots and lots of rings is you have lots and lots of weight. And this big heavy thing would often kind of bend underneath its own weight. He improvised on this. Well, first off, AUB has one of these. Where's that? I'm going to assume you said the right answer. It's on lower campus. I think it's on top of the physics building. We're going to say it is. It's on the physics website for sure. The Brahes only had 1.5 circles and was almost 3 meters in diameter. So you can see there's a picture of it. 3 meters in diameter, almost, or 9 feet in diameter. Here's that half circle he referred to. This was much lighter. He was able to keep it from being distorted, though it was huge. The larger it is, the more accurate and fine-tuned he can make his measurements. As he's tracking the stars through the sky, where is each star every night, its exact location with respect to some sort of fixed points. It was mounted on a self-centering axis. It was engraved using Tycho's transversal method, which allowed scales to be very finely subdivided. It was equipped with sights he developed to eliminate parallax errors. So he's developing new instruments to do his task well. It's not just all concepts that went into the Renaissance. Actual machines helped bring along our understanding of the physical world. And that's not too surprising, because all of our labs now are equipped with modern and advanced machines. We make better lasers now than we ever did, for instance. Now, this particular instrument has been estimated to have an accuracy of 38.6 seconds of an arch. That is roughly 1% of a degree. All right? How many degrees are in a circle? Okay, so take one of those 360 slices and take 1% of that. His tool was accurate within that small percentage of error. This was incredibly fine-tuned for its time. This was vastly more accurate than the sort of charts that we were getting from the Greeks and from, the medieval scientists and those old guys. Okay, so again, this is just a history. So we've got, it's a picture book. Here are some other tools. A lot of these, though you can't tell from the scale here, they're huge. A lot of them are 6 feet in diameter or in radius. The one on the left is called the revolving steel quadrant. And this one was even more accurate than the first one that I showed you. This tool allowed him to get between something like, the other one was 38.6. This one was like 36.4 degrees of an arc. He would often mount them on the roof, or these would be portals where starlight would be able to come in from the underground. All right, here's some other little facts about Brahe. He not only designed and built instruments, he also calibrated them and checked their accuracy periodically. How many of you have ever calibrated an instrument in a lab? Okay, this is one of the first guys who started calibrating his instruments with respect to fixed focal points to make sure that they're not being warped over time. Tycho relied heavily on the then new technique of this long word. It was an algorithm for approximating products based on trigonometric identities that predated logarithms. So he had all this data that he had to then accumulate to figure out where are the stars at any particular place. He had complicated trigonometrics, and what did he do? He used this new mathematical technique that allowed him to do it accurately and quickly. He couldn't have a whole bunch of individuals day and night just doing calculations. They actually needed an updated method for doing this. Now, the Large Hadron Particle Accelerator in CERN, what does it do? I know at least one of you knows the answer. Does it make cupcakes? Does it smash particles together? Courtney? Yeah, smashes particles together. Now, what do? You get a whole lot of data from this. You smash all the particles together, but then what do you do with it? This is what he was doing. He was gathering tons and tons of data. Every sort of important star or planetary, planet, moon, he would track it across the sky, find its exact locations, and do all these calculations to see where it is, how far away it is. Now, what do you do when you have all this data? Well, you need some sort of computer system to actually do the calculations for you. He was doing this. This sort of technique here is what our supercomputers do for us now. Compiles the information in a quick and efficient way and gives us the relevant data. This was one of our first research institutes, and they're doing the very same things that we're doing at CERN. CERN just uses more powerful instruments. In 1572, he refuted the Aristotelian belief in an unchanging celestial realm by using his precise measurements to indicate that new stars, or supernova, actually came into existence. There are actually new stars that were popping in to the celestial spheres. Now, can anyone tell me or suggest why is this important? Why is this interesting that you have supernova, new objects in the heavens, so to speak? Under Aristotle, the heavens were eternal. They never changed. They were made of a special substance that never degraded. They never, nothing ever new came, nothing ever died. The objects always kept a fixed sort of relationship with one another, except for the planets. They were called the wanderers. Here, if you can show that new objects were coming into existence in the heavens, and not just in the atmosphere, they kind of thought these supernova might be objects within the atmosphere itself, not within the heavens. And his precise measurements and calculations showed that they had to be extremely far away, farther than the moon itself, showing that they're in the heavens. So he helped refute the Aristotelian sort of metaphysics about what the heavens were made of. Tycho observed heavenly bodies throughout their orbits. And as a result, so what happened before is you want to know where Mars is. You find Mars on the first day of the month. You find Mars a month later. You find Mars 2 months later. You find Mars once a month. They would find Mars every single night for multiple times during the night. They were incessant with getting as much data and as precise of a data as possible. And because of that, he was able to refute and discover some orbital anomalies that would never have been found. This information corrected documents and data that had been held to be true for 2,000 years. People thought this sort of book of calculations that we inherited from our ancestors was true. He went through and he says, no, this data is wrong, this data is wrong, this data is wrong, and he corrected that book. Now, this was so important because Kepler came along and then organized that data. If Kepler was using a book of bad data, he would not have easily come up with his elliptical orbits. Kepler worked with Brahe, took Brahe's good data, super intense, well-fine-grained data, and then was able to come up with a new model for the solar system. And we said lots of interesting things about Brahe. Most importantly, he had a fake nose made of copper. He lost it in a duel when he was young, and for the rest of his life, he was literally had like this piece of metal on his face. That's not the most important, but it is funny. All right, Galileo, you've already talked about Galileo in the previous lecture, so we're not going to talk a lot about him. Remember, we're focusing on instruments. What was the instruments for Brahe? Brahe had a whole slew of new astronomical instruments. But what was the most important tool that Brahe had? Instrument. What's the most important instrument? The lab itself, right? The very fact that he had a state-funded lab to help him do and document or gain precise empirical data of the stars' locations. Galileo, we know what his instrument was. We know that it was a telescope. The telescope was thought to be invented by Zacharias Janssen in 1608 and the microscope in 1690. The telescope, the first ones, could add about a magnification power of about 3 times. So you can make something 3 times bigger. Galileo stole that telescope. And he built one that was 20 times bigger for magnification. That is a model of his original telescope. Now, what did he do with that telescope? Did he spy on his neighbors, or did he do something more important? Yeah, he looked at the heavens. Someone back there I like, they're talking. He looked at the moon. And what did he discover about the moon? The moon wasn't perfectly spherical. It wasn't smooth. It had all these divots and deviations. And he argued that these divots and deviations were because the moon had crevices and mountains and valleys. And maybe a giant meteor hit it right here. Now, if a giant meteor can hit the moon, and if the moon can be changed, manipulated, then it's not made of an incorruptible substance. It's not made of something that is impervious. It's made of something that's just like Earth. Maybe Earth and the heavens aren't so very different. If the stuff that happens on Earth can happen to heavenly bodies, then maybe we're not made of different kind of stuff. And that was the Aristotelian belief. So seeing this on the moon and making these arguments help supplant that old metaphysics. The sun, turns out, has spots, also thus not a perfect object. Jupiter has moons. Now, the reason why it's important that Jupiter has moons, what is this significant of? Well, in the geocentric universe, what's the center of the universe? What does everything rotate around? The Earth. What do these moons rotate around? They're called Jupiter's moons, so presumably they rotate around Jupiter. So by proving that Jupiter had moons, he proved that there was another source of, center of orbit. And that other center of orbit wasn't the Earth. It loosens our grasp on thinking that the Earth has to be the center of all rotation. Very important. We know that was his tool. His tool is a telescope. We're going through the different disciplines, and we're paying attention to how the tools were used by the scientists, and then how they helped bring about a different sort of understanding of our place in the universe because of it. It wasn't Descartes sat in an armchair, which is fine. He was a philosopher. We love philosophers. And he came up with theories about the nature of humanity and what knowledge and truth is. Here we see individuals using tools to come to a similar understanding, though contrary often in many places to Descartes. So the question is, how is it that we gain information about the world? How is it that those in the Renaissance and in this, going through the scientific revolution gained a sort of understanding about their place in the universe? It wasn't merely by sitting in an armchair. It was by doing calculations and using these new tools. Medicine. So we got this guy, Vesalius and Steno. We already saw Vesalius. And we've already seen the quote by Steno. Let's find out a little bit about Vesalius. They both relied on experimentation through surgery. Surgery wasn't, up until this point, and in particular human sort of dissection, was not a very popular thing. People didn't do it very much. The last great surgeon dissector of human bodies, you might think that it's common sense. If you want to know something about the human body, what should you do with it? Some dissections, right? But what they were doing is they were relying on something like a 1,400-year-old text on human anatomy written by the Greek physician named Galen. So let's talk about him real quick. Galen, 129 to 210. These guys were living in like 1600. This is, in some places, up to 14 and a half hundred years until these guys started doing human dissection and correcting what he wrote. He wrote the textbook that people were using for 1,400 years. They said, hey, maybe we should do some experiments ourselves, see what the human body's actually like, come to have a sort of experimental basis for our knowledge rather than just resting on some sort of 1,400-year-old authority figure. Well, he did get some things wrong, and we're glad that they corrected this. Vesalius, 1514 to 1564, he was a professor of anatomy at the University of Padua, and he revolutionized our understanding of human anatomy. We are where we are now in terms of our understanding of biology and human anatomy, partly because of people like him, who actually just got their hands dirty and didn't take sort of authority. We all have to take authority for granted at some point. We're your instructors. You have to listen to us and we tell you what to believe at some point. But at some point, you have to go and just do the experiments yourself and check that what you're being taught is actually right. That's what they did. It took them 1,400 years to do so, but they did. Now, let's go back. We got two people. We got Vesalius. I haven't talked about Zeno yet. You got Galen. These two guys are 1,400-ish years apart, and yet they're actually twins. I mean, look at them. This is Galen, and that's Vesalius. That's incredible. The two greatest human dissectors. Okay, these are some of the drawings. You could actually still, on Amazon today, buy Vesalius's textbook, and it has all these hand-drawn engravings of what the human anatomy is like. This became the new textbook. People started using his textbook to actually figure out and see what was going on inside of human beings, and then they can make better sort of prognosis when something goes wrong. Here are some of the images that he drew, and he was very gruesome, but detailed. Of particular importance, which he discovered through surgery, is his theory/discovery of the circulatory system. He was able to actually, we have these large veins going throughout our body, and that blood was circulated to our body, providing nutrients to our body, and then circulated back through the heart. At least that was the theory. The problem was, like your hand, it's really hard to see veins in your hand. You like hold up to light and you can kind of see hands, like veins in your hands. But the theory says that each part of your body has veins. It's hard to see veins in the very small, fine parts of your body. So people didn't really believe his theory for a while. His theory was based on experimentation, but his experiments could only go so far to see all the small veins in your body. What did we need to wait for? Well, his theory was confirmed by this gentleman, Malpighi. He uses a microscope in 1661. We already said that the microscope was made in 1590, but wasn't put into like important biological use. Might have been important in other uses, but not biological use, until 1661. And he uses it to see the blood capillaries and to confirm that blood was in fact in circulation, even in the fine small parts, even in the layers of your skin of, your epidermis here. You have little fine capillaries going through everything. Now, we could not have known this. We could not have confirmed the sort of circulatory theory of blood until we actually used the microscope to confirm these things. Our advancements in our understanding stemmed from the different tools that we used and an insistence that experimentation was a key to our understanding of the world. This is going to sound kind of obnoxious to you and maybe simple. We know that experimentation in our culture is important, that you actually have to go and test things to see whether or not they're true. But remember, we are now living on the back end of the scientific revolution. This is on the front end. This understanding of the way knowledge is gained wasn't quite accepted yet, or there are debates about it. We shouldn't take that too much for granted. All right, Steno. This is a dissected shark head. He was one of the other first great dissectors of animals. He was a paleontologist and a geologist. Steno lived in 1638 to 1686. He was an atomist, an atomist, not an atomist, and then whatever. He studied anatomy, paleontology, and geology. And he came up with an important discovery. He was doing a surgery on a shark. He found these teeth, and he's looking at these teeth. Now, he was also a geologist, and there are these stones that were called tungstones. And tungstones are this like fossilized rock, and they didn't really know what it was, so they called it a tungstone. And he was comparing tungstones to shark teeth. And he said, hey, these tungstones aren't rocks, they're shark teeth. They're just fossilized sharks. Now, this is crazy. You're finding tungstones buried in layers of rock on top of mountains. Who's going to believe you that these are shark teeth? Well, he thought they were shark teeth. He argued that they were shark teeth. And he, in a sense, is the father of modern geology precisely because he started this idea of stratification, that things can be stratified. He had this theory about how fossils are made, et cetera, et cetera, et cetera. This is one of the first indications that, that animals came about through evolution and that the Earth was actually much older than what had previously been thought. Okay, what else did he do? Now, this might not be so interesting to some of you, but Descartes had all kinds of theories about different things. Descartes thought that tears came from liquid in your brain that would drain out through your eyes. Why he thought that, I don't quite know. Descartes also thought that the soul lived in the pineal gland. Now, the pineal gland is a particular gland in your brain, and humans' souls kind of rested in there. And it was through the interaction in the pineal gland that the soul had access to the brain. Like, how does the brain and the soul interact? Well, through the pineal gland. Now, I know you guys are laughing, but this is what I thought. Now, only, according to Descartes, and people before him, only men were rational animals. Only men had souls. If the soul lives in the pineal gland, then can a turtle have a pineal gland? Well, presumably not, because the pineal gland was made for an interaction between the soul and the brain, right? So animals can't have pineal glands. Only humans have pineal glands, because the pineal gland is the way in which the soul interacts with the brain. But Steno finds out that both these things are false. Tears are not liquid draining from the brain. Pineal gland can be found in many animals, so it's not the seat of the soul. And he found out this was Galen and Descartes also thought that the heart was like a little heat engine. They thought that the heart was the place of warmth, where warmth was generated from. What did he find out? He says, no, just do a dissection of a heart, and you'll see it's a muscle. And it's got 2 valves and pumps, and it pumps stuff around. You have all these theories about what the body is, and you're going to get them wrong unless you actually just do experiments on bodies. This you might think is obvious. It wasn't so obvious back then, that you couldn't just come to have knowledge of the world just by sitting and thinking in the chair. Which tools have we had so far? We had labs, telescope, give me one more, microscope. We also had some mathematical techniques that we talked about when we talked about Brahe. Let's talk about electricity. Let me check my time. Okay. William Gilbert was the first great electrical engineer. He was the father of systematic study of electricity. He built the first electroscope, which he then used to discover which objects could be made to hold a charge. So the idea is they knew that some objects could be made to hold a charge, but they didn't know what kind of objects. So he made this electroscope, and the way the electroscope works, it's rather simple. It's a piece of metal, and if you have a charged object, it'll pull the electrons, the free electrons in the metal, along the end here. The positive charge will then pile and push itself at the back end of it, and thereby, so if you've got a charged object here, the electrons will kind of attract these electrons, and it will pull the arrow towards me, and the butt of the thing will be pushed away from me. So it will point at whatever objects are electrified. Very simple tool. What did he do? He did something that like Brahe did. Brahe did not come up with a theory of how the planets orbited one another. Brahe collected data. He said, here's a list of data, as fine-grained and precise as I can make. This is what Gilbert did. He says, he doesn't end up having a theory for what electricity is or what produces electricity. He comes up with a list. Here's a list of all things which can be made to hold a charge. And then he has some gradations, how easy or how difficult it is to make them hold a charge. While he didn't devise a theory to explain his findings, it was a good example of how science was starting to change by incorporating empirical studies at the dawn of the age of reason. Moreover, he theorized that the Earth was a giant magnet with 2 poles. I mean, that's pretty impressive. He's some guy in England with a little electroscope testing rocks and stuff, and he theorizes this giant globe that we live on is a magnet with two poles. Fascinating. Let's review. Let's see if we can get this in order. We know what age the telescope and the microscope were made. Let's see if we could remember which came in which order. What was the very first scope of these three? Well, there's four, but we haven't talked about the fourth yet. What's the first? I heard telescope. I heard micro. It's actually the electroscope. The electroscope was 1600, and that was by Gilbert. What's the next scope? I got telescope, microscope. I hear telescope. Telescope is next, 1609. Technically, the microscope was made first, but wasn't put to biological use until after. Microscope, 1661. Who knows what this last scope is? It was made in the 1750s, and it's called a sneakoscope. And it was made to discover sneaky wizards. This is apparently true. Okay, what we see, we had four tools, four guys. That was a Harry Potter joke. If you're confused with a sneakoscope, don't go looking for a sneakoscope. So you have four scopes, three of them are real, and you see how each one of them was important for advancing our understanding of the physical world. We shot down philosophical principles through dissections of human bodies. We shut down Aristotle through our use of the telescope and Brahe's labs. Let's talk at the last section. We got two sections, but the last one before we move on to the scientific method is chemistry. Now we got two individuals here, and these ones are fascinating. The study, I have to say, of chemistry was very, very closely connected with the study of electricity. And nowadays, you will often, if you're an electrical engineer, you probably have to know some physics, right? So also, the study of these two fields were intimately connected with one another. So I have Boyle up here at the top as one of our chemists, but he was also a great researcher into electricity and magnetism as well. Otto van Gulik is credited with inventing the first air pump. But you guys should write this guy's name down. He's interesting. His main job, he was a mayor of a town. He discovered some interesting things about an air pump, and then he just went around and showed people. He was like a circus. He went from town to town showing people his air pump and how the interesting things you can do with an air pump. Such a pump, first invented in 1654, would make a vacuum in airless space. Let me see if I want to talk about that. Okay, so yeah, it says. Now, if you make a vacuum in an airless space, this is both philosophically and scientifically important. It's scientifically important because of the sorts of experiments you're able to do without air. You can see, what does air affect? Philosophically, it's important because the philosophers were debating whether or not a vacuum was possible. Descartes thought that space and matter were identical. There isn't one thing called space and another thing called matter. Like, you might think that you're sitting inside of an auditorium, you're filling space in some sense, but for Descartes, space just is extended matter. There's one thing. Everything in the universe is just filled with matter, and everything's just bumping together. Okay? It's just one globular thing moving around. But if you can make a vacuum, then that means you have space with no matter. And you could shut down or refute Descartes' theory. They were able to make a vacuum, at least insofar as a vacuum is characterized as having no air. Whether or not there's other particles inside could be debated. Everything that has been proven by experience or sensory perception should be preferred to any plausible or brilliant conclusions, as a lot of things seem to be true by thinking or speculating, but finally cannot be proven in practice. What we see here is we see a moving away from pure intellectual speculation to a requiring that our beliefs be established, at least in some regard, on actual empirical data. This sort of spirit here, you're going to take for granted. Don't take this for granted. This came about through a revolution, through the Renaissance. This is a gift that our culture now has, the fact that we require detailed experimentation for our beliefs about things. No matter how preferred or plausible and brilliant the conclusions, even if you could sit and do philosophy and come up with brilliant and plausible solutions, we should be a little skeptical until we can actually have some experimentation to help back it up or provide support for it. All right, let's tell some stories. It's fun stuff. So if you are in a submarine and you break the window, what's going to happen? I hope we all know. You're doing this. The water is going to come in. Now, why does the water come in? Because the pressure on the outside is heavy. There's a lot of pressure pushing in, and we have very little pressure pushing out. Okay? If you take the submarine further and further down, what happens? It's going to crush. Now, once the submarine has been crushed, all the windows are open, the water comes in, does it continue to crush this thing into like an atom-sized square, or does it stop crushing it once all the water fills the cavities? Because now the pressure has equalized. What they discovered is when they pumped out the air from these different vessels, they found that spheres were good, they reduced the air pressure on the inside. So like the water on the submarine that's pressing on the outside of the container, what's the air now doing? The atmospheric air is now pressing on the outside of the container. They've sucked it out, and all of a sudden they realize, hey, this thing's stuck together. Why is it stuck together? Because the atmosphere is holding it together, pressing it together. Just like if you were trying to open a door underwater, you would have the whole atmosphere you'd have to push against. So he loved doing this Gurik guy. He would take one of these spheres, pump as much of the air out of it as possible. Now there's a pressure difference. So there's all this atmospheric pressure pushing these two spheres together, and he would tie up teams of horses and go to different villages and say, I bet your horses can't pull this thing apart. There's no bolts, there's no glue, there's no nail holding it together. And people are like, what are you talking about? Of course my horses can pull this thing apart. What's holding it together? The atmospheric pressure itself. So you could suck the air out of here, and then you could like hang weights. The pressure of the air on the outside is working against these weights to hold it together. We'll talk about this one and the next one. I'll point this out. There's a little bell. This is one of the famous experiments that Boyle did. Remember, these are tools. These simple things, a vacuum pump, is going to be very important for our understanding of gases, of sound, of light, of electromagnetic forces, and you just made a vacuum pump. He put a bell inside of a vacuum pump. Let's talk about it. Boyle, 1672, he came up with Boyle's law. Pressure times volume is a constant. He did this, and he did this precisely. He knew that this was the case because he had a air pump to do fine-grained experiments, seeing how much water and how much pressure, or like what volume of air and what is its relationship to pressure. He was able to do these experiments precisely because he had an air pump. Now, PV equals a constant was speculated. People had thought about this before him. He was able to come about and prove it using a sort of fine-grained pressure air pump. Ooh, let's go back. He was like the father of mathematizing chemistry. He gave precise mathematical formulas to sort of qualitative laws about the gases. This is a mathematical model for how gases operate. And he was one of the first people to start doing this. Okay, let's talk here. You've got a bell. Now you all know, how does sound work? Is it like magic? Vibrations through air, you know this. They did not know this. Now, if you didn't, you all know this. You've got the answer. I'm going to ring the bell and then slowly pump the air out. What should happen? Should you hear the bell? No, because you have no air to vibrate for the sound to vibrate through. They didn't know this for certain, but they tested it. They put the bell in. They had a magnetic device on the outside that would like ding it with a piece of metal. So there's a magnet on the outside. They would then use that magnet to ding the metal. And as they pumped the air out, they would no longer hear the vibration of the bell. So they concluded a couple of very interesting things. The first one is that sound consisted in the undulation of air. Second, that light does not use air as a medium. How did they figure that out? How do they know that light wasn't using air as a medium? I can only hear people in the front rows. You might have an answer in the back. Anyone in the front know? Well, a guy over there, what is it? Can you yell? Yeah, you can still see through it, right? The bell may have dimmed, but did our image of the bell dim? No, you can still see it perfectly. Light was still passing in and out of the jar, though there was no air, right? If light required air to transverse through the atmosphere or through space, then as you suck the air out, light wouldn't be able to go through in or out of it. It'd turn into like a dark cavity, or maybe it'd just reflect off the surfaces. But that didn't happen. The next thing is that electromagnetic forces does not use air as a medium. We know that precisely because the magnet still worked. Right? The magnet still works, though there's no air as a medium. What this means is that whatever light is, it's not using air to propagate. The first thought was that air used this other thing called the ether. And this ether was something like air, but really light and insubstantial. Is that true? Well, I'll take some other experiments to say it's not true. But I'll take some, that won't happen for many hundreds of years. Okay, now, we've gone a long way. We've found many, many instruments of the scientific revolution. We found many, many instruments that were part of the Renaissance, making the Renaissance possible. This might be the most important tool or instrument that made this all possible. When you think of an instrument, you're going to think of a telescope. You think about a microscope. You're going to think about the sneakoscope. You're going to think about an air pump. But this is probably, you might even think about a lab, but this is probably the most important tool. Francis Bacon, he came up with the Novum Organum Scientiarum, roughly the new organ of science, or the new instrument of science. When you think about a new instrument of science, you're thinking a new contraption. That's not what he meant. Francis Bacon, 1561, 1626, he was an inventor of the Baconian method, or the scientific method. He wrote this book, the Novum Organum Scientiarum, 1620. The new organ for science is not a new instrument, but is found in his book. The new organ for science is the scientific method itself. It's this insistence that when you do experiments, you have to use induction. You have to do careful experiments. What did we see Brahe do? Did Brahe like doing the experiments in his castle with the instruments in the air? No, because of all the perturbing factors. He sunk it into the ground. We must take care in how we do our scientific experiments. He said you must have a great skepticism regarding one's own work. Don't believe what it is that your theory is. Try to disprove your theory. Try to see maybe how you didn't take everything into account when coming up with your data. He had a reductive approach. When you, nowadays, this is common. Most of our physical world, we're trying to reduce to physical laws. He had a reductive attitude where he tried to explain what was true in the world by reducing everything to as fewest elements as possible. How many elements are in string theory? 1. And everything gets reduced to the properties of the string as it vibrates. He had this reductive approach, which he sort of gave a philosophical background for. He was contrary to Descartes and Aristotle. He said, look, if you want to come to have an understanding of the world, you cannot trust just sort of philosophical investigations or reflections. You must actually get out and just test things in the world. Your senses can be trusted, your mind cannot. You might justify anything with philosophical reflection, but the world itself will tell you what its nature is. So he argued that method was needed because of the natural biases and weaknesses of the human mind, including natural biases as it has to seek metaphysical explanations which are not based on real observations. He said, he loved physical senses and distrusted that the mind alone could ever get to truth because of what he said as intellectual obfuscations or intellectual idols. Now, he is called the father of empiricism. So this is a standard encyclopedia entry. He's called the father of empiricism. Sir Francis Bacon is credited with establishing and popularizing the scientific method. Okay? This is where we're going to be a little bit critical. One of the tools, a very important tool, is the scientific method. This idea that we ought to trust and rely on experimentation for forming and developing knowledge of the world. The question is he the father of the scientific method? Another quote by Thomas Young, which was an old school physicist, he said, Bacon first taught the world the true method of the study of nature and rescued science from that barbarism in which the followers of Aristotle, who's a follower of Aristotle? Descartes, and this guy, I'm a philosopher, right? I'm a barber. I'm a barbarian. In which the followers of Aristotle, by a too servile imitation of their master, had involved it. He says, Bacon rescued the world from this sort of thinking. He invented the scientific method. Now let's review some things. Human dissection happened in 1530. Why? Because they didn't want to take Galen and Descartes and Aristotle's word for granted. They said, we must do the experiments ourselves. That was in 1630. Ehrenberg and Sternborg, 1581, very similar reasons. Detailed, precise, empirical observations are required for an understanding of the physical cosmos. That was in 1581. The electroscope, 1600. The telescope, 1609. Then comes Bacon. Bacon doesn't write his book until all these things were already happening. He's saying, guys, you guys should really care about experiments. Don't you think they knew that? Look at this. Air pump, 1654. The microscope, 1661. Now let's remind ourselves. The electroscope, right here. This was by that Guericke guy. The Guericke guy. Here's his quote, right? Remind yourself. This was 1600, and the Novum Scientiarum came out in 1620, 20 years later. He writes this 20 years before Bacon wrote. Everything that has been proven by experience or sensory perception should be preferred to any plausible or brilliant conclusions, as a lot of things seem to be true by thinking or speculation, but cannot finally be proven in practice. He was already doing the scientific method before Bacon. So what I'm trying to say is the scientific method was about. It was the spirit of the age. It was this distrust of just mere speculation and this sort of impetus that we must check the world, we must do experiments, and we must be careful about them. Now, Bacon came along and kind of wrote it all up for everyone. He synthesized it. He made philosophical arguments for it. But it was already about in the culture of the Renaissance. Now, we are done, right? We all have to leave. We have places to go. Let me close us off with two small quotes. Remind ourselves. We have been talking about Francis Bacon. He's the father, supposedly, of the scientific method. Here's a guy, Roger Bacon, no idea why they had the same last name, but they both said very similar things. This guy said it 400 years before Francis Bacon. He says, the strongest arguments prove nothing so long as the conclusions are not verified by experience. Experimental science is the queen of sciences and the goal of all speculation. He says, for if any man who never saw fire, okay, think about a man who never saw fire. Pretend that you've never seen fire. Proved by satisfactory arguments that fire burns. Let's say that I convince you. You've never seen fire. I convince you that fire burns. Like, okay, you convinced me that fire burns. I've never seen it. I don't know what it is, but you tell me it burns. His hearer's mind would never be satisfied, nor would he avoid the fire until he put his hand in it, that he might learn by experiment what argument it's supposed to teach. All right, so we're basically done. The idea here, though, is that we have many tools for the Renaissance. We have many instruments for the revolution that came about during the Renaissance. You have tools that are made out of glass and metal, microscope, telescope, air pumps. You have other tools like scientifically funded research labs that came about, at least one of the first ones. You have mathematical tools that allowed for the sort of summary of a lot of empirical data. You also have philosophical conceptual tools. So let's summarize that real quick. You've got tools, you have scopes, you have labs, Ehrenberg and Sternberg. You have methods, you have surgery. So look at surgery came about. This is the method. This is the way of engaging with the human body. You also have this mathematical technique that was very important to Brahe that came about. And then finally, you have a theory, the Novum Scientiarum. This is a theory that encapsulated how it is that we ought to interact with the world in order to gain an understanding of it. All right? So we're basically done. You guys can go on your way. Keep these things in mind. The instruments of the revolution are these. Some of them are physical, some of them are conceptual. And that's all.